Hi, and welcome to the final lecture of the course Machine Learning. And in this short video, I'm going to talk about dimensionality reduction. Uh, Modern machine learning algorithms, such as ensemble algorithm, neural networks, could actually handle very well the high dimensional examples. It could be sometimes up to million of features. And with modern computers and graphical processing units, GPUs, dimensionality reduction techniques are used less in practice than in the past. Today, the most frequent use of dimensionality reduction is data visualizations. As you know, us humans can only interpret on a plot of the maximum 3 dimensions. So anything more than that, we don't have any understanding of what that could be and how to even visualize it and further interpret it. So one of the basic use cases of dimensionality reduction is basically where we want to either visualize a data set to start processing with, or sometimes even the output of a, for example, clustering model. We want to see how different clusters are located and if we could get anything meaningful just by looking at the visualization. There is another situation in which we could benefit from dimensionality reduction, and that is when we have to build an interpretable model. And to do so, we are limited in the choice of learning algorithms. For example, we can use decision tree learning or linear regression. And by reducing the data to lower dimensionality and by figuring out which quality of the original example uh, and is really contributing to what our model is predicting, and that is why it is important to use a lower dimensionality. And basically, these are the two use cases that are widely used these days. Uh, in other words, we can say that dimensionality reduction removes redundant or highly correlated features, and at the end, you really don't need all the correlated features to be part of your modeling process. It also reduces the noise in the data, and all that contributes to the interpretability of the model. And it is important when interpretability is an aspect that we are looking for. There are 3 widely used techniques for dimensionality reduction. One of them is principal component analysis, in short PCA, and you probably have heard a lot about it, and we're going to discuss about it a bit in this video as well. Another one is uniform manifold approximation and project, or in short UMAP, and autoencoders. We already discussed a bit about the autoencoders in previous lectures. Basically, you can use the low dimensional output of the bottleneck layer of an autoencoder as the vector of reduced dimensionality that represents the high dimensional input feature vector. But for now, let's get to the 2 techniques that we haven't talked about them yet in this course. And the first one is principal component analysis, or PCA, and this is one of the oldest dimensionality reduction methods. And I'm not going to go through the math behind it. I'm only going to provide some intuition and using an example telling you how it works. Consider the 2-dimensional data that we have here on figure A. Principal component analysis are vectors that define a new coordinate system in which the first axis goes in the direction of highest variance in the data, and the second axis is orthogonal to the first one, as you see here in picture B. So if our data was 3-dimensional, the third axis would be orthogonal to both of these 2 things. And in figure B, the two principal components are shown as arrows, and the lengths of arrows reflect the variance in this direction. Now, if we want to reduce the dimensionality of our data, basically changing the d, which is our original dimension, to the d nu, we pick the d nu largest principal component and project our data point on them. For our two-dimensional illustration that we have here, we can say d nu to be 1 and project our example to the first principal component to obtain the orange points in figure C. So basically converting from two-dimensional to one-dimensional. And to describe each orange point, we need only one coordinate instead of two. The coordinate with respect to the first principal component. And when our data is very high dimensional, it is often the practice that the first two or three principal components account for most of the variation in data. So by displaying the data on a 2D or 3D plot, we can indeed see a very high dimensional data and its properties. So this was in short about principal component analysis and the logic behind it. Basically, we look at the components with the highest variance and we project more or less all other data points in those 1, 2, or 3 dimensions. Another popular method is UMAP, and you need to keep in mind that the idea behind many of modern dimensionality reduction algorithms, especially those designed specifically for visualization purposes, such as UMAP, is basically the same. We first design a similarity matrix for two examples, and then for visualization purposes, besides the Euclidean distance between two examples, this similarity metric often needs to reflect some local properties of the two examples, such as the density of other examples around them. Yet again, I'm not going to go through the mathematics that is a bit involved here, but this is basically the idea. We put together things based on the similarity metric. Here you can see in this picture the result of the dimensionality reduction applied to the famous MNIST dataset of handwritten digits. We have already seen the different example using MNIST throughout this course, and you can find many other examples online. But this is where we apply different types of dimensionality reduction on that. And keep in mind that MNIST is commonly used for benchmarking various image processing systems, and it contains 70,000 label examples, and 10 different colors on the plot correspond to the 10 different classes. Also, each point on the plot corresponds to a specific sample in the dataset. And as you can see, UMAP separates examples visually better. Remember, it doesn't have access to the labels. So in practice, UMAP is slightly slower than PCA, but faster than autoencoder. These are probably the things that you need to keep in mind when you're deciding which one you want to go with. And before closing this short video, I want to say a few words about outlier detections. After all, if you manage to do the dimensionality reduction and do the visualization of your dataset, you potentially could see the outliers. But what do we mean by outlier detection? Outlier detection is the problem of detecting in the datasets the examples that are very different from what a typical example in the dataset look like. We have already seen several techniques that could help to solve this problem, like autoencoder or one class classifier learning. If we use an autoencoder, we train it on our dataset, then if we want to predict whether an example is an outlier, we could use the autoencoder model to reconstruct the example from the bottleneck layer. The model unlikely be capable of reconstructing an outlier. And in the approach, when we're using one class classification, the model either predicts the input example belongs to the class, or it is definitely an outlier. So by that, I close this video here, and let's jump very briefly into the coding of uh, dimensionality reduction. I'm going to show you very small examples in the next video. See you there. Hi again. As promised, in this video I'm going to show you how to do dimensionality reduction using PCA and UMAP. And for PCA I'm going to do dimensionality reduction on the famous iris dataset that we have used as the example throughout the course multiple times. So I'm going to import pandas to deal with the data frame, and then I'm going to basically get the data frame. And indeed, this is the data set we have been working with throughout the course in multiple examples. So what is going to happen here is, first I want to normalize the values in the data set, because this is how PCA works best. If you have different scales, it won't probably be as efficient. So don't miss this step when you're using PCA. And then that is done. And for the visualization purposes, I want to do PCA in a sense that I want to have only two principal components. And it is quite easy. I import PCA from scikit-learn decomposition, and then I basically define how many components I have in mind, and then I use PCA on the dataset, and I built a new data frame here. Let's see how this one works. Okay, now you see that, as I said before, I have two principal components for each of my examples. And what I'm doing here, I'm going to basically concatenate the labels, the outputs, to the data set, and I'm going to plot it here. And you can see that you could visually see that how these three types of irises are plotted on this screen. And iris setosa is more or less better distinguished from the other two. They still share some borders together, but you could have an understanding of where in the 2D plot each of these examples could sit. And UMAP is also done on MNIST, and it's not really anything complicated that I'm going to do here. I'm just importing the package, and I'm running it on the data, and I'm plotting the data. The whole point of this video, and then I'm going to upload this code in the GitHub as well, is that for you to know what to use when you want to do the UMAP reduction. And also remember that for your mini project 3 you need to do a bit of dimensionality reduction, so it's good to know where to look for it. And again, I am going to get the data set from the scikit-learn datasets in the MNIST, and these are the plotting things, and of course I'm going to import UMAP. You need to install the package if you don't have it on your computer, and then get the data set and apply UMAP on it, and then plot it. And this will probably take a bit of time to be plotted. Yeah, so I will continue the video after a few moments. Yeah, it's done, and you can see that clearly it have clustered it had built different clusters, and it is easy to see by dimensionality reduction the data of MNIST. So this was our last hands-on practice. We continue with the rest of the lecture today, and I really wish you good luck with your final mini project. Bye.